So to obtain IL min, we go for high VD. Why high VD? Because duty cycle will be low, and this lead to go to the discontinuous conduction mode. I have formula here. I have everything, VO, VD, D, okay, TS I calculated, output I calculated. Let me find out. Then it's merit of doing, let me say, math. Now, many applications for this is available. In my book, Photovoltaic Power System Prospects, and I use this converter. You see here, power converter, to supply the power coming from the solar cell to the grid or to a DC load, okay, by converting it to a DC load. Now we control the DC-DC converter here by controlling by using digital controller. This is another block diagram representing the PV, the charger controller. They call it charger controller, and MPPT, maximum power point tracking, okay, where DC-DC converter here, it could be step up, step down, step down, step up. We may provide some part of the power to storage battery, and some part will go to inverter. We will explain inverter soon, to convert it into AC and inject it into the grid or to the load. You can see here, this is one of the converters, and this is the load, this is the PV. Or another way, this is the PV charger control. We go to the load, or we give it to battery and battery through inverter to the load. Now here we can see that the characteristics of current and voltage, we can control them by controlling the pulse width modulation to find the base situation. Different characteristics here are applied. I don't want to talk more about this now, but just to give you a brief, the one of the application of DC-DC converter. Our students in the previous year, they did this. Okay, you see here single phase rectifier here, as you can see here, supply with the rectifier, and then we have here the converter, DC-DC converter, and here the load. They build it, as you can see here, or in this another circuit, and they try to take measurement of the input, output, current and voltage respectively. You will find this converter is in the market, it's very cheap. You can find it and use it for any application. Now for step up converter, the same discussion will repeat it here. So it's easy. But the only difference is the operation, how it operates. Now you may ask, okay, if I have a 12 volt battery, how can I supply the load from 12 volt to make it 18 as example? From where it gets improved? The connection here. We use the same inductance, diode, capacitor, and the switch, but rearranging them and connecting them in different way. Now at the beginning, as you can see here, this inductance, when we close the switch here, the current will follow through the inductance back to the supply. Look like the circuit in this way. The load is only connected to the capacitor. The diode here will not be connected because short circuit before it. Okay. What we did is we store energy here in the first half part. When T on, we store the energy. Energy increase here, and the voltage of the inductance is equal to the supply voltage. The second time, when we open the switch here, the supply will send its energy, and there is inductance contained energy will also release. So from here the improvement came. You see here, inductance releases its energy, and the voltage will be VD minus VO, similar to the book converter. As you can see here, the circuit is similar to the book converter in the conduction mode. Okay. Now if I come to find the driver formula, I will say output for the voltage will be VD at T on and VD minus VO at T off equals 0. Rearrange, we will find the relationship between output to input is 1 over 1 minus D. In book converter it is D, which is less than 1 always. Now if D here less than 1, 1 minus something less than 1, less than 1. 1 over less than 1 greater than 1. So always output greater than input. Also, we assume that the circuit is ideal, lossless, so input equal output. We can use it to drive formula for the output current with respect to the input current. Again, we need to discuss the situation of continuous and discontinuous mode. We use the same graph. You see here the voltage is changed, okay, and the graph changed now. Have a look here. Let me start with IL boundary, which is 1 over 2 IL peak, as we discussed before. Now we can have a formula. Again, we have, you remember, VL equal L di over dt, cross multiply, integrate, you will get this value. Now T on is dTs, okay, this one is dTs, and we can change Vd into Vo. We know Vo over Vd equal 1 over 1 minus d. We can substitute for Vd by its value. We are here. Now if I sketch this equation on the graph here, you can see this is ILB. It's peaked at 0.5. So if I substitute for D here by 0.5, I got the maximum boundary inductance current. I can re-substitute here to express it in terms of maximum current. For output boundary, now difference between output and output here, we can substitute the formula, repeat the same discussion, but substitute here in terms of D. We can find that it is 1 minus D squared by D. Okay, now let me sketch this one, this formula. I sketch it, it become in this way. It peaked at 1 over 3, 1/3. Okay, you see, 1/3. So IOP max become, after I substitute here and here by 1 over 3, we got this expression. Let me substitute it back here. We got formula of IO boundary in terms of maximum IO boundary. Now the same thing could be repeated for book here in boost for the discontinuous conduction mode. The same graph, as you can see here, the period is delta 2 TS where the current is 0, and we can derive formula. VL is VD for this time and VD minus VO for this time, as you can see here. I rewrite it again. I got formula for output with respect to input in the discontinuous conduction mode, which consider the off time, part of off time where there is current. And I can use the assumption that input equal output power. Then I can find for current another formula. Now if I go to sketch the relationship, I did the same thing to find D in terms of VO over VD and IO over IOB max, and I sketched there D with respect to normalized current and change in normalized voltage. We can see here line for constant is continuous conduction mode, while here these curves, okay, is discontinuous conduction mode, similar to the discussion for boost converter. Let's use this in this example. In a step up converter, the duty ratio is adjusted to regulate the output voltage. This is output voltage, okay. The input voltage varies in the range of input voltage is changed now. The maximum power output is given 120, okay. So for stability reason, it is required that the converter always operate in discontinuous conduction mode. The switching frequency is given 50, so I can find time 1 over 50 kilohertz. Assume ideal component and C as very large. Calculate the maximum value of LS that can be used. This is opposite the previous example. It was the minimum value, now the maximum value. Have a look. IO max can be calculated because he gave me power and voltage. I got it. For relationship between output to input voltage, we have VO over VD 1 over 1 minus D. So let's substitute, considering that input voltage is 12 ones 36. So I got two values for the duty cycle. Okay. Now what he told me, highest inductance. Highest inductance, okay, the current will be small, right? The current will be small. So which one you will select? This D 0.75 or 0.25? Just a minute, let me see the graph here for output. For 0.75 current is lower than for 0.25. Sorry, 0.25 here. So definitely I will use the higher D. There, okay, I will use the higher D. I will substitute in this equation. I have the equation. Just let's substitute to find L. It's found to be 9 microhenry. One more issue is the ripple. ripple in the circuit. By the way, in ripple in the circuit, we have to consider the effect of parasitic elements. Parasitic element, if we sketch VO with respect to VD with D, when we change D, we don't expect that the curve will be going up. And sometime it will go down. Why it go down? Because when we deal with the capacitor or inductor, we assume that they are pure capacitor or inductor, which is not the reality. In reality, the inductors have its own resistance and capacitor. The same thing for capacitor, its own resistance and inductance. Plus, in the circuit, there are stray inductances and stray capacitances. For that, we have to consider this. Now, for ripple, if I sketch the current of the diode at the beginning, when the switch is on, have zero current. When the switch is off, it take the output current in this way. If I sketch, okay, this one here, this delta Q equal this delta Q. If I want to find delta V, it will be delta Q over C from the definition of capacitor voltage. Now, this delta Q is time from here to here, time by the average, which is IO. IO by the time T on, which is DTS. Very simple equation. We can use it and to calculate the ripple. And don't forget that capacitor value specify how much ripple we have. I will stop here. I'm looking forward to see you in the next session.